Good afternoon, my name is Suraj, and today we will be walking through the final for Spring 2016's iteration of Data 8 here at Berkeley. So let's get into it. So the first question is our programming question, and we're given two tables, one called Cafe and one called Price, and we're asked to write code that answers the questions that are provided. So the first question asks us to write a line of code that tells us the total number of views of the cafe named Nafali. Well, if we look at this table right here, we want the sum of the numbers 37 plus 75 plus 50. Of course, we don't want to hard code that. We just want to write it in terms of general code. So how can we write code that will approach this, right? We just want the sum of these three numbers. Well, we know that if we do cafe.where the name is Nafali, that's going to give us just these three rows of the table, right? So that's a good first step. Not the brood row, just these three. That's a good first step. Now what do we want? Well, we know that each cafe has three types of reviews, right? A 3-star, a 4-star, and a 5-star review. And we want the total number, right? So we want the sum of these three numbers. So if we do .column count, this will give us an array of just 37, 75, and 50, which will be the number of 3, 4, and 5-star reviews respectively. And if we take the sum of that, that will give us the number of reviews total for Nafali. So that's kind of the first question. The second one asks us for the total number of reviews of the cafe with the fewest reviews, right? So now we ask ourselves, how can we, go about approaching this? Well, we want the total number of reviews for each cafe, right? So we want some sort of chart that looks kind of like this: name and count. So for example, we'd have like, Nafali, and this here would be, 37 plus 75 plus 50. We'd have brood, and so on and so forth. And then we want the minimum number from here. So what function do we know will do this for us? Well, that's the group function, right? So if we do cafe.group by the name, we know that will give us the that will group by the name column. And now we don't want to average the different count values or average the different star values. We want to add them up, right? So we do sum. And now in this case, each of these rows will also have a stars column, each of which will be 3 plus 4 plus 5, which is 12. I mean, that's kind of meaningless, but we don't have to look at that, right? We only really care about the count column. So if we do this, we'll reduce to this table right here, and if we take the count column from here, dot column count, this will give us the total number of reviews. This will be an array of the total number of reviews for each of the different restaurants. And we take the min of that, it'll give us the number of reviews of the cafe with the fewest reviews, which is kind of what we want. The third problem asks us for the average number of stars for reviews of the cafe named Nafali. So what's the average rating that Nafali got? And this question, lends itself towards finding the weighted mean. Right. We have 37 threes, 75 fours, and 55s. What's the average number of those, right? Well, so first they give us the hint to us that we would like to use a helper line to make our second line of code a little easier, right? So what we'll do there is we'll say n is equal to cafe.where the name is equal to Nafali, because the rows where Nafali is not involved are kind of irrelevant in this problem, right? So now what exactly are we looking for, right? We kind of want 37 times 3 plus 75 times 4 plus 50 times 5. I don't know why I said those backwards. Over 37 plus 75 plus 50. So this is the same way you'd calculate your GPA or variation as we've done in this class before. This is a weighted mean, right? So on the numerator we multiply the number of times a certain value appears times the value itself. So 37, 3, 75, 4, 55. And on the denominator, we just sum up the total numbers of values, right? So in total, we have 37 plus 75 plus 50 reviews. So we kind of want to replicate that here with this being our numerator and this being our denominator. So we know that our denominator right off the bat will just be the sum of the count column, right? Because again, we've reduced ourselves to having only this part of the table. So the sum of the count column will just be 37 plus 75 plus 50, which is what we want. But on the numerator, though, we want the pairwise product of the stars column and the count column. So we just write that line in as well. So we do sum of n dot column stars times n dot column count. And that will, as we've gotten used to, multiply those values pairwise. So we're good to go. Now problem 4, or part D, I guess, asks us for the total variation distance between the distributions of stars for Nephali and Brood. So let's remind ourselves, what does the total variation distance mean? If we have some set of values x1, x2, and so on to xn, we also have the values y1, y2 to yn. The total variation distance in this case would be the sum of the pairwise absolute values. So that would be x1 minus y1 plus x2 minus y2 plus so on and so forth till xn minus yn. All of that divided by 2 times 0.5. That is the definition of the total variation distance. So we know that we have this 0.5 times out in front, so that kind of reminds you of what total variation distance is if you kind of forget on the exam. But I believe it's a thing that you should put on your cheat sheet if it's not already on the one that's provided. So let's write some starter code or some helper code that will help us out in the last line. So we know that one of these lines will correspond to Nephali and the other one will be to Brood. We can do cafe.where, again, name is equal to Nephali. But in this case, we really only care about the count column, right? We don't really care about the stars themselves. We know that the first value will correspond to 3 stars, second to 4, and third to 5, right? We don't need this column anymore, right? So we're only going to look at the count values, so like x1, x2, and x3 will be count for Nephali. y1, y2, y3 will be count for Brood. So we can do dot column count, and we're good to go. Same for Brood. Okay. Let's get some water. Okay, so we want the total variation distance between the distribution of the stats for Nephali and Brood. So what that means is we don't want, as I mentioned earlier, x1 to be straight up 37, x2 to be 75, and x3 to be 50. We don't want that. We actually want, by distributions, they mean we want the proportion of 3-star, 4-star, and 5-star values, right? So instead of x1 being 37, we want it to be 37 over, I believe, 162, which is the sum of 37, 75, and 50. Instead of x2 being 75, we want 75 over 162. And similarly, we want 50 over 162. These are the proportions of 3-star, 4-star, and 5-star values, or in other words, the distribution of 3, 4, and 5-star reviews for each of the restaurants. And we would do the same thing for the Brood values as well. So how can we go about doing this? Well, let's kind of fill this in from left to right. We know we're going to be taking the sum of some absolute values, right? And now in here, we have to specify what the difference we're going to be taking the absolute values of is, right? So that will be of A over sum A. So that will take on the values here, here, and here, minus B over sum of B, right? And so this looks kind of weird, right? Because, sum of A is not going to change, right? If we look at x1 versus y1, x2 versus y2, x3 versus y3, sum of A is always going to be equal to x1 plus x2 plus x3. but the value of A itself will change depending on if we're looking at the first pair, second pair, third pair. So this might look a little weird to you if you've done a lot of practice and kind of paid attention to the little details throughout the course. Maybe it won't, but this is how this should be implemented. And maybe if you need to look further into this kind of total variation distance calculation, maybe you should. So part E asks us for an array containing the names of all cafes that have above average coffee prices. Right. So now we're going to have to start using this second table. So first, how do we find the average coffee price? That's not too bad, right? We can just say np.average. This is called price.column $. And that will be the average coffee price, right? So that's just the number. Sorry. So now if we do price.where the cost column is greater than this average value, we'll get a list of all the names, right? So that's exactly what we want, because we don't have to do a join yet, because this column or this table already has all the names. We're just looking at purely the prices. So again, we're going to do price.where price.column $, is greater than whatever we found here. np.average or np.mean price.column $. Oops, it's a little messy. And we're good to go. So hopefully that makes sense. We're just taking the price column or the price table where the cost is greater than the average. And oops, we forgot. Now we need to take the name column from here. Column 0, just to save a little bit of space. But we only want the names, right? We don't want the entire table. Now part F, we're going to need a join, as it kind of tells us. But we want, among all the reviews of cafes with $3 coffees, we want the proportion that are 3-star reviews. So, before we start writing the code, let's try and visualize exactly what it's asking of us. So we want the number, sorry, not the number, but we want the cafes with $3 coffee. Not the cafes, sorry. The reviews of $3 coffee that were 3 stars over the number of reviews of $3 coffee. Right. So we want the proportion of 3-star reviews of all the reviews of $3 coffee. So in this case, for example, we know that Nefali has $3 coffee, so we're going to consider it. Well, what are the total number of reviews of Nefali? Well, that's 37 plus 75 plus 50, right? And what proportion of those, or what amount of those, were 3 stars? Well, that's 37. And the reason I'm writing all these values on the left is because we'd also have to add up the next, the sum of the reviews of Brewed, and then the total number of 3-star reviews of Brewed, which would be 56. You have, 56 plus 71 plus whatever, and so on and so forth. So in the numerator, we're going to take the count values of the places that have 3 stars that have coffee that costs $3, and on the denominator, for all the things that cost $3, we're going to add up all the count values, not just the 3-star ones. So kind of complicated, but once you kind of get what the question's asking, it's not too bad. So the first part, we have a join, as the question kind of hints to us. Well, we kind of need to join together these 2 tables, right? So, and the way we're going to join them is by the name. Nefali, Brewed, whatever, right? That's how we're going to join them. We're going to do cafe.join by the name table, or name column, sorry. And the second argument is the second table, right, which would be price. Now, we only care about the places that have $3 coffee, right? Like, for example, Abe has $2 coffee, so nowhere does that factor into this calculation. So we can kind of drop that. So we only want where oops, price is $3. So now we need to kind of replicate the sum we have over here, right? So on the numerator, we want $3 coffees, three-star reviews. The denominator, we want all the reviews of $3 coffee. So on the denominator, which is a little easier, we can just do j.column count, which will have, these values and these as well, because they all correspond to the number of reviews of $3 coffees, or $3 coffees, sorry. And on the numerator, we're going to have the same thing, but j.where the stars are equal to 3. And then we want to do the count column of that. The column count. And that will give us, 37 over 37 plus 75 plus 50, and so on with all the other values. So hopefully that makes a little bit of sense. Wow, this looks really messy. Hopefully you're able to follow along. And lastly, before we get into, some of the more stats questions, we have a question where we kind of need to replicate this table. And so if you see, before, Brood, Nafali, and all those values, they were the headers of the rows, right? Or they were row values. But now instead, they're the titles of columns. So we need to think to ourselves, what function, converts from row types to column types, and that is pivot, right? So pivot can take either 2 or 4 arguments. If we recall, the first one is the new column labels. The second one is the new row labels. And the optional third and fourth are the values and the function applied to the values. Okay, so we need to see, what are our new column labels? What are our new row labels, right? So, well, the columns clearly are what the name column was before, right? So that will be what our column labels are. Secondly, what are our row labels? Well, they're based off of the stars, right? Because before, stars just happened to be one of the columns, but now they're the beginning of the rows. So we'll put stars in here. Now, if we just left it at this, then we would get the same table, but instead, all these values would be 1. And why is that? Because 5-star Brood, that's one possible combination. Like 4-star reviews of Nafali, that's another possible combination. So we kind of need to specify which values these cells need to take, right? And in this case, these values are coming from the count column from before. So we kind of need to specify that. And lastly, we need a function to apply to these. And in this case, for each individual cell, this is a weird concept to wrap your head around, but for each individual cell, if we apply sum to the array, 56, it's just going to be 56, right? If you sum just a number on its own, it's going to return back the same number, which is what we want, right? Because, and the same thing, if you average a number on its own, it'll give you back the same number, right? And that's what we want, right? Because we're already specifying that we want the count values. We don't want any other function applied to these values, right? We just want to specify that count should be the values. So we can put any function here. I'll just put sum for now. But you could also put, np.mean, np.sum. As long as it's not something weird that would change the value. Like if you did cosine or something. I don't know why you do that, but that would change these values. But sum or mean, that will give you these values that we want. And that wraps up the first question. Okay, now it's time to get into problem 2, which deals with our understanding of histograms. And these questions, at least for part A, are multiple choice, I guess, where you pick either A, B, C, or D, where A represents the first quantity is larger, B, the second quantity is larger, C is that they're about the same, and D is that there is not enough information, to answer the question. Okay, so the first question asks us what's larger, the number of unmarried women between 25 and 29, or the number of unmarried women between 30 and 39. So one important realization to make is that since we're looking at the unmarried bar graph, or sorry, unmarried histogram, in both cases, the number is equivalent to the proportion, right? Because we're going to be taking percentages of the same number, right? Since there's 400 unmarried and 100 married, right? So we can just look at the proportion, i.e. we can just look at the areas of the histograms, right? So now let's look at the values for both 25 to 29 and 30 to 39. So again, we need to look at the areas. So for 25 to 29, the area, well, the width is 5, the height is 1, 2, 3, 4, 5, 6, so that's 30. So about 30% of the values lie between 25 to 29, or i.e. 30% of the women who are unmarried are between 25 to 29. So now we need to look at 30 to 39. So here the width is 10, the height is 3, and that's also 30, which also tells us that 30% of the unmarried women are between 30 and 39. So the question's asking us which quantity is larger. Since they're both about 30%, we kind of have to say that they're about the same. So C, both approximately 30% of all unmarried. And that's more than sufficient. Part B, or the second question, sub-question, asks us, among the unmarried women, the proportion who are 25 to 29 versus among the married women, the proportion who are 45 to 49. Well, so here we're asking about the proportion. So we just ignore the fact that there are 400 unmarried and 100 married, and we're looking at just the percentage, right? So we already found the proportion of unmarried women who are 25 to 29, right? And that was 30%. Now let's look at the married women 45 to 49 category, right? Here, the width is 5, the height is about 5, and so that means that's about 25% of all married women are between 45 to 49. So that leads us to conclude the answer is A, since 30% is greater than 25. And that's it. Now we need to look at the number of unmarried women aged 30 to 39 versus the total number of married women. And we can do that, right? So we know that in total there are 100 married women. And now we need to see the women unmarried 30 to 39, how many of those exist? Well, the proportion would be 10 times 3, which is 30%. But looking at the proportion is not enough because we want the number. So we want 30% of the total number of unmarried women, which is 400. So that gives us 3 out of 10 times 400, which is equal to 3 times 40, which is 120. So that means there's 120 unmarried women between 30 and 39, and there's 100 married women total. So which number is larger? Again, that's A, because 120 is larger than 100. And that's it. So now we want the proportion of married women aged 30 to 34 versus the proportion of married women aged 35 to 39. So here, we've kind of come to the first kind of question where we don't necessarily know the answer, right? So we look at the bins and we say that the bins are 25, 30, 40, 45, and 50. So you know that here, even though the axis may lead you to believe that 30 to 35 is one bin and 35 to 40 is another one, if you look at this array, it tells us that that's not the case, and that this is actually all one bin. And as we learned before, you can't, make assumptions about the data within a bin, because, who knows? Maybe all of the women who are between 30 and 39 were actually between 30 and 34, and there's nobody who's between 35 and 39. Like, we don't know. So there's nothing we can really say about data within a bin. So this would be a question where we answer D. Can't answer within a bin. And that's it. The last one asks us to compare the 20th percentile age of unmarried women versus the 20th percentile age of married women. So remember, the concept of a percentile refers to the percentage of values that are at that value or below it, right? So 20th percentile means you want to find the age such that 20% of women are that age or younger, right? So we kind of want to find that kind of marking somewhere on the unmarried list and the married list, or the histograms. So we know that 30% of the data, 30% of women are in this bar, right? So that means the 20th percentile has to lie somewhere in this bar. You know, at some age between 25 and 29, there's a woman such that 20% of the women are younger than her or as old as her. You know, it can't be anywhere here because the second that you're 30 years old, at least 30% of the values are less than 30, right? So we know that the value has to be somewhere between 25 and 29. Somewhere in this interval. Whereas the same value for the married woman, we know that this bin here only corresponds to an area of 5 times 2.5, which corresponds to 12.5, I believe. So that means only 12.5% of women who are married are between 25 and 29. So that means, by default, the place where the 20th percentile married woman would have to be somewhere in this bar, right? Because this contains the next 40% of values. So somewhere in here will be the 20th percentile value. But that interval is 30 to 39. And we know that regardless of which value we pick in the 25 to 29 interval, it has to be less than the value in the 30 to 39 interval, right? So we know that by default, the second value is going to have to be larger, right? So we know that this has to be B, since 25 to 29, whatever value we pick in there, has to be less than whatever value we pick in here. And that's about it. Part B asks us, what proportion of everyone surveyed were in the age range 30 to 39? Well, let's try and calculate that. So what we want on the bottom is a total, and on the numerator we want number 30 to 39. And, well, how can we find the number of people who are 30 to 39? Well, we know that here, 30% of the women were between 30 and 39. And here, 40% of the women were between 30 and 39, just by looking at the areas. So that this calculation will now be 30% of 400 plus 40% of 100, all divided by 500. And that will give us the proportion of women who are 30 to 39 of everyone surveyed. And as we discovered before, 30% of 400 is 120, 40% of 100 is 40, and we're dividing this by 500. So this yields 160 over 500, 8 over 25. That's a good enough answer for this. 8 over 25. And, you know, you'd write some of these calculations over here. You know, 120 plus 40 over 500 or something like that. And that will give us the proportion of women who were surveyed in that age range. Okay. If you select a woman randomly, uniformly at random, and find out her ages between 30 and 39, what is the chance that she is married? So this kind of is a conditional probability question, right? Where we want the probability that she is married given she's 30 to 39. Well, as we learned, the rule for conditional probability is that this would be equal to the probability she's both married and 30 to 39 over the probability she's 30 to 39. Right? So let's try and calculate this. Well, we knew from before that how many women were 30 to 39? We just found it out here, right? That was 160 because that was 120 plus 40. So that's 160. And of those women, how many were married and 30 to 39? Well, that was the value we got here. It was 40% of 100, which was 40. So we have 40 women were both married and in the age range 30 to 39. And 160 women were in the age range 30 to 39. So that means 40 over 160 will give us the value you want, or 1/4. And that just about wraps up the second problem. Let's continue with problem 3, which deals with correlation and regression. Part A asks us, what is the value of correlation of lead, IQ, and BLL? So notice in the table provided we have correlation of BLL comma IQ, or we can say correlation of X, Y. And the question is asking us for the correlation of Y, X, right? And you know, they hint to you that the correlation functions appears on your midterm study guide, and the reason for that is because the correlation of X and Y is equal to the correlation of Y and X. Because remember, the correlation coefficient is taken by taking the mean of the products of X and Y values taken in pairs in standard units, right? So since it's a product, it doesn't matter if it's X and Y or Y and X. So this will be the same value, minus 0.1. Excuse me. So the next question is, what is the estimated average IQ of a child with a BLL that is 2 standard deviations above the mean? So for this one, it's pretty convenient to consult our cheat sheet because there are several formulas that we can use with regards to regression, right? And the one we want to use for this one is Y in standard units is equal to the regression coefficient R, the correlation coefficient R times X in standard units, right? And an expansion of this formula is given by, you know, estimate of Y minus mean of Y over the standard deviation of Y is equal to the same thing with X, right? R times X minus the mean of X over the standard deviation of X. But this entire thing, X minus the mean over the standard deviation, that's the same thing as X in standard units, right? So we can kind of use this formula to try and figure out what the estimated IQ of a BLL that is 2 standard units above the mean. So let's go ahead and try and do that. So we know that the Y value that we're looking for minus the average value of Y, which is provided in the question, which, of course, in this case, Y is IQ, so that's 100. Sorry, not 100. Yeah, it is 100. Over the standard deviation of Y, which is 15. That is equal to the regression coefficient, correlation coefficient, negative 0.1, times X in standard units, which is 2. Right, so now we want to solve for Y, and that will give us our estimated average IQ. So Y minus 100 is then equal to negative 0.1 times 2 times 15. So then Y is equal to 100 minus a tenth of 2 times 15. And we know 2 times 15 is 30, so this whole thing is 3. So our estimated IQ then is 97. So, you know, we'll show a little bit of work here. We have Y is equal to 100 minus 0.1 times 2 times 15 is equal to 97. So we kind of could have done part B after doing part C, and then finding the blood lead level value that was 2 standard deviations above the mean and substitute that into our regression line. We could have done that, but this way was a little quicker, and we have a formula to, you know, calculate this kind of thing directly. But just so you know, there are different ways that you could do this question. Part C asks us for the equation of the regression line itself. So for this, if you don't have all the formulas memorized, the cheat sheet comes pretty handy, right? So in this case, what is our slope? Well, it's equal to R times the SD of Y over SD of X, right? In this case, which that is minus 0.1 times the standard deviation of the IQ values, which is 15, over the standard deviation of the blood lead level values, which is 2. Okay, and that ends up being negative 1/10 of 15, 1/10 of 15 over 2, and that simplifies to negative 3 over 4. So that's our slope. So we know Y is going to be negative 3 over 4 X plus something. Now our Y-intercept is equal to the average of Y, which again was 100, minus the slope, which is negative 3 over 4, times the average of the blood lead levels, which was 6. So this ends up being 100 plus 18 over 4. This is 9 over 2, which is 4.5, which is 104.5. So we can rewrite this as negative 0.75x plus 104.5. And that would be our equation of the regression line. Part D asks us to complete the code so that the last line right here prints out a 95% confidence interval for the IQ value of the IQ value corresponding to someone with a blood lead level of 10.0 on the regression line. And then we want to use our sampling techniques, and we know that we have the slope and intercept functions defined on our midterm study guide. Right, so we know that we need to pass something in to the slope function, right? And the slope and intercept functions, they take 3 parameters. So the first one is the table from which we're going to sample. The second is the x column. And the third is the y column. So we know whatever table we're passing in to slope and intercept, we're taking the first column to be the x and the second column to be the y, which is where we got the 0 and 1 from. 0, 1 corresponds to 1 and 2, right? So we know if we look at this table right here, the lead table, the first column corresponds to blood level and second column corresponds to IQ. So we know that we're probably going to be passing in this table. And since here we're sampling from this table, we're going to have to put R here instead of hard coding in lead. So that's R. And we know that our estimate is equal to the slope times the value we want to estimate, or the x value we want to estimate, plus the intercept. So it's y equals mx plus b. So here we're going to have a 10.0. And then we're going to append to our estimates table our new index, right? So this table is going to look like our estimates table. Will look something like this. Resample, number, and estimate. We'll have, 0, 1, 2, 3, all the way to 399. And then these will have some estimated values. Who knows what they are, but it will have some values. Right, now, we want an array of our estimates, right? We don't want it to be in the form of a table. So what we want to do is just take this column right here. So estimates is equal to estimate table dot column. We can do dot column 1 or dot column estimate. And we're good to go for part D. Now part D really tests our knowledge of confidence intervals. So some of these are very tricky. So make sure you know your confidence intervals and their definitions very well before trying to attempt this kind of question. So the first two ask us if our confidence interval contains most IQ scores, so around 95% of IQ scores in the population for children with a blood lead level of 10.0. So for in the population and in the sample. And the answer for both of these is false. The reason that is because we need to look at what the definition of the confidence interval says, right? So we know that a confidence interval just tells us that our estimation technique is correct 95% of the time. It tells you nothing about there's a 95% chance that a certain value is in this range, or 95% chance that this encompasses the mean of something. All we know is that a confidence interval, the confidence level, tells you that your estimation technique is right 95% of the time. It tells you nothing about the actual scores. So that's where these questions get kind of tricky. These are both false. Now here's an interesting question. If width replacement equals false were used in line 3, the interval would have 0 width. And that one is going to be true. And to kind of see that, we can talk about the example of sampling from a deck of 52 cards. So if we were to sample from a deck of 52 cards without replacement, we draw a card, write down what the card was, and then not put it back in the deck, then by the 50-second sample, we will have sampled the entire deck, right? And we will have gotten one of each card, since there's no possibility for repeats, right? But if we allow, if we do sample with replacement, then there's a chance of getting 2 6 of hearts, or 3 kings of hearts, right? There's a chance of repeats occurring, and more likely than not, repeats will occur, right? So if we sample without replacement, i.e., if this were false, then we're just going to regenerate the exact same lead table that we had before, and the estimate would be the same estimate as we plugged in here. So there would be really no range for a confidence interval. Like the left endpoint and right endpoint would be the exact same value, right? The whole reason of getting these samples is that we'll get a slightly different table each time, with some repeated values and some omitted values, right? And that's how we create our confidence interval. But if we're not, sampling with replacement, then we're just going to get the exact same table as before, and the interval, both the left and right endpoint, will be the exact value of the estimate. Now, true or false, if the study were repeated many times, most confidence intervals computed in this way would overlap. And that again, is true. And that's true because what does a confidence interval tell us? It tells us that 95% of the time, our estimation technique is correct. So if that's true, then when we repeat this estimation technique several times, then we'd expect that the intervals overlap, right? Because if they're correct 95% of the time, it should contain the same values most of the time. If the study were repeated many times, the average IQ in the population would fall within most intervals. That's false. Because, again, this question only deals with values of a blood level of 10. And we have no idea whether or not this is the average. This corresponds to the average IQ value or not. Right? This question is not dealing with the mean of the entire data set. It's just talking about specific blood lead level of 10. So that's going to be false. But the last question, if this study were repeated many times, the average IQ in the population for children with a blood level of 10, that would fall in this interval most of the time, because that's exactly what we're computing each time, a confidence interval for exactly this quantity. So that wraps up the true and false questions here. Part F asks us, what null hypothesis would you evaluate in a statistical test to determine whether blood lead levels and IQs are negatively correlated in the population? Right, so we kind of have this notion that the null hypothesis and alternative hypothesis are complements of one another, right? So if the null hypothesis says one thing, the alternative hypothesis says the exact opposite thing, right? So if we want to try and prove that something is true, then that thing we're trying to prove is our alternative hypothesis, right? That means the null hypothesis has to be the exact opposite of that. So if we want to try and discover to see, or trying to run an experiment to see if BLL and IQ are negatively correlated, then our null hypothesis is exactly the opposite of that, i.e. what we already believe to be true. And that would be that BLL and IQ are either positively correlated or not correlated at all. So our null hypothesis would be that R is greater than or equal to 0. And instead of R, you could also use slope, because the relationship between slope and R is just some positive constant. Right? And that would be our null hypothesis. And then if our alternative hypothesis ends up being true, then we can say that R would be less than 0. Part G asks us, based on the summary statistics provided, what is the minimum proportion of IQ scores in the sample that are between 70 and 130 according to Chebyshev's inequality? So remember, Chebyshev's inequality says that at least 1 minus 1 over k squared of the values are within k standard deviations. That's what Chebyshev's inequality tells us, right? And now, the interval 70 and 130 they give us is actually very convenient because, well, for IQ at least, because the mean is 100 and the standard deviation is 15, right, as we see here. So that means 130 is 100 plus 2 times 15, and 70 is 100 minus 2 times 15. So conveniently, 70 is 2 standard deviations below the mean, and 130 is 2 standard deviations above the mean. So we want to find at least what percentage of data falls within 2 standard deviations of the mean. And by this inequality, 1 minus 1 over k squared would be 1 minus 1 over 2 squared, which is 1 minus 1 over 4, which is 75%, or 3/4. So by Chebyshev's inequality, 1 minus 1 over 2 squared is equal to 75% of values within 2 SDs. And that's just by Chebyshev's inequality. The last part asks us, just based off of the scatter diagram and the summary statistics, what proportion of values do you think are actually within this interval, 70 and 130? So not just like ignoring Chebyshev's inequality, which is true for things that are not just normal. We want to look at, okay, what's something else we can include with this interval, right? So if we look kind of here, all the values are concentrated. If you look at in both from left to right and top to bottom, all the values are concentrated in the center, with fewer and fewer values out to the edges, right? And what kind of distribution that we know is similar to that? Well, that's a normal distribution, right? Normal distributions, fewer values at the tails, and everything's kind of concentrated in the middle. So if we hypothesize that this distribution is normal, then we know that 2 standard deviations corresponds to 95% of the data, right? As we've, kind of repeated in this class over and over, 95% of data is within 2 standard deviations. So we would estimate that 95% of the data is between 70 and 130, or i.e., 95% of the scores, IQ scores, are between 70 and 130. And so those are 2 different ways to approximate the number of IQ scores in those ranges. And that wraps up number 3. Okay, so problem 4 deals with, some experiment with fish trying to, determine the impact of lead on the fish's IQ, and it's a hypothesis test and permutation test question. Okay, so some guy, he puts a bunch of fish in a bowl, lets them sit, then puts a divider in between them, and puts a lot of lead on one side of the bowl and not the other, and these are the results he gets. Right, so we have one table, and these are grouped in different ways. Right. So the first question is asking us to complete the null hypothesis in this experiment. Right. So far we haven't really proved anything. So the null hypothesis would have to be that adding the lead, doesn't really impact anything, or the distribution of the IQs should be the same whether or not lead was added, right? So we can try and fit that null hypothesis to the blanks that we're given, right? So among the fish in the experiment, the distribution of the IQ scores. The distribution of the IQ scores of the fish with none exposed to lead is the same as the IQ, the distribution. The distribution of the IQ scores had they all been exposed. So what we're saying is that the distribution, had none of them been exposed, and the distribution had all of them been exposed, the IQ distribution should be the same. And that's our null. So the second question tells us that our test statistic is the absolute difference between the IQs of the fish that were exposed to lead and were not exposed to lead. So an example here would be the absolute value of 113.9 minus 94.6. So we're not looking at whether or not adding lead makes the fish smarter or dumber. We're just looking at, is there a difference, right? So then our test statistic in this case would be this difference. So now, given a table, we want to kind of calculate those values, right? So how they generated this table in the example was they just grouped by the side and np.average. So we can do that. So you can say t average is equal to t dot group by side. We pass in np.average or np.mean, and that will give us this kind of table. And then from there, we take the differences of the averages. Oh, this also should be dot column 1, right? Because we only want the right side. And then, so we'll get these values, and we take the np.diff of those and take the first item, because the first item the 0th element item will have the difference, and that will be good for that question. And then second to last, we have to complete this permutation test function, which will return a p-value from a permutation test. It takes in a generic table and a test statistic function f. So In this case, we're not hard coding with the fish table and the absolute difference of averages function. We're just going to code it in terms of some general table T and some function f, right? So this is from Spring 2016, and the way the data science package was used was slightly different there, right? Here, stats, which is where we keep track of all the values we get each of our 1,000 iterations, was a table, and we appended to a table. We don't really do that in the Spring 2017 iteration, or who knows when you're watching this. But so in our case, this should be an array. Right, and this would be appending to an array. There's a minor difference, and so you should expect to see an array as you're used to. But anyways, R, the table that they're creating, X and Y. X will be the same, same column as the side column in our example, right? So it's left, right, left, and so on and so forth. But the Y values, since we're doing t.sample column 1, will be the fish IQ column, but just completely resampled, right? So shuffled in some different order. So maybe we'll get like 105, 98, 118, who knows, right? Maybe this will be 118 as well, like who knows, right? So this will be some sampled version, right? And now the statistic we want from that is just the absolute difference between the IQ of the fish on the left and the right. And that's where we go ahead and call this function now, f. Right, so we're going to append to stats this function f called on this resample table R. And that will append, so now this table stats will keep track of all the differences, right? And now to calculate our p-value, we need all the times that stats were more extreme than the observed value, right? Because our p-value is always the probability of our observed, our observed value occurring, or something greater, or something more extreme than that occurring, right? So what would that be? Then in this case, we would want the case where stats.column 0, again, this is kind of weird because of the old syntax, was greater than f of t. And f of t would be the probability, f of t would be this difference here, right? And so now this will give us the probability, or the number of times, rather, that in our 1,000 samples, that the difference was this value or greater. It was greater than 103.9 minus 94.6. And the probability, we divide always by the number of trials that we had, which would be 1,000. And here, nb.count, non-zero, more extreme. So again, more extreme will be an array of all the times where the test statistic, i.e. the difference, or the absolute difference between the IQ of the fish on the left and right, exceeded the difference that we observed in the table T, which in this case would be this, right? And then we count the number of times that happened, divided by 1,000, and that's our probability. And so lastly, circle true or false, assuming the fish are randomly distributed. A p-value of 0.003 indicates that lead exposure causes a change in IQ. Well, the only way we can conclude this is if we have some sort of reasonable p-value threshold, which is usually 0.05 or 0.01, and this value is significantly less than either of those cutoffs. So we know that we're probably gonna make some sort of conclusion, but also we knew that this has to be a randomized control trial, as we learned earlier in the course, and it appears to be a randomized control trial. So since 0.03 is less than 0.005, yes. So then now in this case we have to reject the null hypothesis, and that means there is some sort of change in IQ. And that wraps up this problem. Okay, now we're on problem 5, the sampling and probability problem. For each of these, the first 3 at least, we need to choose A, B, C, or D. A is almost always true for any uniform random sample with replacement. B, almost always true for large uniform random samples with replacement. C, never true, or D, none of the above. So the first one, it's saying, is the total variation distance between the population and the observed sample distribution, will that be small? And now we need to pick one of these options. And, we look at the central limit theorem, and it tells us that as our sample size increases, that our sample distribution our empirical sample distribution will approach the population distribution. And so that's only true for large uniform random samples, not necessarily true, for small samples. So that's going to be B. Only true for large samples. The second one, for quantitative data, the sample average is an unbiased estimate of the population average. Well, yeah, we've been using this as a basis for a lot of our statistics throughout the course, and this is always true, regardless of if we have a big or small sample. So that's going to be A. And then lastly, this is the one that's a little tricky. For quantitative data, a histogram of the values in a sample will have a bell shape. So if you pull up the cheat sheet that's provided with the final, or you look at your own cheat sheet, you see that if we have a large random sample and we look at the means or the sum of the values that are being sampled, the means or the sum will form a normal distribution, a bell curve shape. But the values themselves, there's nothing said about the values themselves. It's only the means of the values or the sums of the values, right? So that's where it's a little tricky. So it's not almost always true in either of these cases, but it's also not never true. So it could be true in some cases, right? It really depends on the distribution of the population. Maybe the distribution of the population was already normal, so the histogram of the values will also be normal, right? So again, the central limit theorem only deals with means and sums, not the values themselves. So this would be D. None of the above. So that's central limit theorem. And so that's one of the finer details that we need to worry about. So the next part, never mind, yeah. So the next part, we have to write some Python code to compute these probabilities. Just to make it a little easier, we'll say that n is equal to t.num rows, just in terms of our visualization. Okay, so the first one, we're sampling without replacement. What's the probability that row 10 appears in the first 20 sampled rows? Well, since we're sampling without replacement, right, essentially this is just picking 20 random rows from the table that has at least 20 rows. And what's the probability that row 10 is one of those 20? Well, there's 20 rows in total. There's 20 rows that we're selecting and n total. And that's just about it for this one. That's the probability. You can liken it to what's the probability that the ace of spades is one of the first 20 cards you pick. If you pick 20 cards out of a deck of 52 cards, again, that's also 20 out of 52. Same kind of thing. The second one, we're sampling with replacement, so repeats are allowed. What's the probability that row 10 does not appear amongst the rows? Well, since we're sampling with replacement, since we can have repeats, each case, each row can kind of be interpreted as its own case, right? So whatever probability we determine, for the first row, we can apply that again for the second row, third row, fourth row, since, repeats are allowed, right? So the probability that row 10 is the first row, that's 1 over n, right? So the probability that row 10 is not the first row would then be 1 minus 1 over n. Row 10 is not first row. And then we can apply that for each of the rows, right? So there's a 1 minus 1 over n probability, it's not the first row. 1 minus 1 over n probability, it's not the second row, so on and so forth. So that'll just be 1 minus 1 over n to the exponent 20. So in that case, our probability will be 1 minus 1 over n star 20. Make that a little more clear. 20. And we're good to go. So lastly, what's the probability that all rows of T sample 20 with replacement is true, so a sample with replacement, are different? So what's the probability that every single sample is different, i.e. what's the probability it looks the same as sampling with the replacement being false. So this one is where it gets a little tricky. So what's the probability that the first row that we sample hasn't been seen before? Well, that's just 1, right? Because it's the first row. We haven't seen it yet. So now what's the probability that the second row has not yet been seen? Well, there are n rows total, and there are n minus 1 rows that are not the first row, right? So the probability that the second row has not yet been seen is n minus 1 over n. So similarly, the probability that the third row has not yet been seen is n minus 2 over n, because there are 2 rows that have been seen, the first and second, and there are n total. So it's n minus 2 over n. And we can keep doing that all the way until our 20th row, which should be n minus 19 over n. So our probability is then n minus 1, n minus 2, all the way until n minus 19, all over n to the exponent 20. So that's what our probability is. Now it's up to us to try and figure out a nicer way to write this in terms of like a single Python expression, right? Well, so another way we can kind of rewrite this is, just completing this off, n minus 19 over n, would be 1 minus 0 over n, 1 minus 1 over n, 1 minus 2 over n, all the way until 1 minus 19 over n, right? Just a little bit of manipulation. So this is the exact same product that we had before. So now how can we use our array operations to recreate this? Well, that would just be 1 minus np.arange 20 divided by n. So if we were to call just this line on its own, we'd recreate the array that we have above. 1, 1 minus 1 over n, 1 minus 2 over n, so on until 1 minus 19 over n. It's similar to how we have done earlier in the class. So now we know that that will be our array. 1 minus np dot arange 20 over n. Now we need some sort of function, to go through and multiply all these values together. So you could do a for loop or np.prod, which, np.sum sums together the values in an array, np.diff gives you the pairwise differences, np.prod, gives you the product of all elements of the array. So this expression in here will create the array we want, which will be the product of these 20 different probabilities, and then np.prod will give us the product. And that is problem 5. And lastly, we have ourselves a classification problem, number 6. So here we're classifying squirrels based off of some scale of how clean their fur is and how much they weigh, and we're going to classify them as either a pet, I don't know who has pet squirrels, people maybe, I don't know, and wild. Okay, so it's a pretty simple model. So the first question asks us, what is the distance in this feature space between the bottom left unknown squirrel, so that's this guy over here, and its nearest neighbor? Use both features, show your work. Okay, so the key to solving this problem is realizing that the scales are very different on the horizontal and vertical axes, right? So on the horizontal scale, each line, I guess, or each major tick mark represents a change in 2 units, whereas vertically, each major tick mark only represents a change in 0.1, right? So even if 2 line segments appear to be the same length, their different distances will be very different because of the different scales, right? So with that in mind, it's pretty easy to see that the closest neighbor to this guy will be this pet squirrel right here, right? And the reason for that is, well, they have the same x-coordinate, right, which is, approximately 1. And this guy over here, it's located at about 0.35 on the clean first scale. And this guy is about at, 0.12. So their distance will be, 0.35 minus 0.12, which is 0.23. And, this is the same as if we plug it into the formula, 1 minus 1 squared plus 0.35 minus 0.12 squared. It just gives you 0.35 minus 0.12. So it's the same thing, right? And we see that pretty quickly, that this will be the closest neighbor to the unknown squirrel in the bottom left. So for example, the next closest dot to it would be, this guy over here. And if we wanted to calculate that area, well, the change in weight, or in the x-axis, 3 minus 1, right? So this is about at 3, this is about at 1. 3 minus 1 squared. And here, the y difference would be, approximately 0.1. So let's say this is, 0.22 minus 0.12. So now we're going to have to find the square root of, 2 squared plus 0.1 squared. And whatever that is, it's the square root of 4.01 or whatever. That's much greater than 0.23. And all the other points will have greater area. So we'll say that this area, or not area, distance is 0.23. So how would each unknown squirrel be classified by a one nearest neighbor classifier that uses only the clean fur feature on the vertical axis? So what it's kind of asking us is ignore the weight, i.e. just project everything onto the y-axis. What are the nearest neighbors, right? So the bottom left unknown, it's pretty clear that the closest thing vertically is this one wild squirrel here. So this guy will be classified as a wild squirrel. And for this unknown one, well, it has the same y coordinate, or about the same y coordinate as this pet squirrel here. So this one will be classified as pet. Okay. Part C, on the top of the scatter plot, or at the scatter plot, circle the 3 nearest neighbors in the training set to the bottom left unknown squirrel, using both features to calculate the distance. Okay, so this one, it should be no surprise now that these 3 will be the 3 closest neighbors if we're going to use both features. And the reason for that is, as I said, the closest neighbor in terms of going horizontally away would be this guy right here. Let's erase some circles. The closest neighbor would be this guy, right? And it has a distance of, this is some number that's greater than 2, right? Because it's greater than the square root of 4. So it has to be greater than 2. Whereas here, the distance is, this is only 0.23. The y value of this is, approximately 0.65. And this guy's slightly more than that, say 0.75. Right, so these distances, 0.75 minus 0.12, that's 0.63. And, whatever this is, 0.65 minus 0.12, well, that's 0.53. Those values are much less than 2, right? So that means these 3, these 3 are by far the closest neighbors, to the bottom left, squirrel. So that's our answer there. And again, it's very misleading because of the scale, but that's just how it is. And so that's the answer for this one. I guess we can say that's done. And true or false, every possible pair of feature values would be classified as wild for a 9 nearest neighbor classifier in the set. Justify your answer. Okay. So the answer for that one is true. And the reason for that is that regardless of where, you introduce a new unknown squirrel, of its 9 nearest neighbors, at most 4 of them can be pets, right? Maybe none of them will be pets. Maybe 1 of them, maybe 2 of them. But, if you put it in such a way that its 4 closest neighbors are pets, the other 5 closest neighbors will all be wild, right? And then if you take the average of those, or the classification that has the most neighbors associated with that, it's just going to be wild. Right, so no matter where you go, you're going to have at least 5 out of 9 nearest neighbors be wild squirrels. So therefore, in the scheme, you're forced to classify everything, as a wild squirrel if you're using 9 nearest neighbors. So that's the end of this problem, and that's the end of the exam. So good luck in studying, and hopefully this was useful.